Okay, let's get started. Balanced parentheses. So consider the following recursively defined language L over this. So if this looks a little bit confusing, that's okay. It looked confusing to me at first too. But this is basically just defining an alphabet, where your symbols are the open paren and the closed paren. So to make it clear, I'm going to make the symbols blue. So we've got a recursively defined language, which means we've got some recursive rules. The first rule is that open paren, closed paren is an element of our language. The second rule is that if we've got some string x that's in the language, then open paren x closed paren is in the language. And the last rule is that if you've got two strings, x and y, that are in the language, then by concatenating them together, xy, that string is going to be in the language. So let's go ahead and give these rules some names. So this is our base rule, this is our wrap rule because we're wrapping string x, and this is our concat rule because we're concatenating two things that were in the language. So the claim we're trying to prove now is that these three rules create exactly the set of balanced strings of parentheses. So proving this claim can really be broken down into two parts. The first part is really figuring out what the heck a set of balanced strings of parentheses really means. So in other words, we have to give another non-recursive definition of a balanced string of parentheses. Once we have that, then we can go ahead and prove that L is that balanced string of parentheses. In other words, prove that a string x over this given alphabet is an L if and only if it satisfies the definition we give in part A. So let's go ahead and get started with part A. So we want to give a non-recursive definition of a balanced string of parentheses. Since the given language was called L, let's go ahead and call our definition of the language K. So it's going to be a set of strings that satisfy some properties that we have to come up with. So intuitively, you probably already have an idea of what a balanced string of parentheses looks like. You've seen it in code, you've seen it when you're writing down math formulas, but you might not be able to think of exactly what properties make a set of strings balanced and what makes them unbalanced. So a good starting point to come up with these properties is doing some examples. So here's a good moment to pause and try and come up with the properties yourself after trying a few examples. Okay, hopefully you've thought a bit. Let's try and do some examples together. So a good starting point is always the empty string. It's the most basic string. So you could argue that the empty string is balanced. You could argue that it's not balanced. In our case, because the original language L did not include the empty string, we're going to want to try and match that, so the empty string is not going to be in our language K. Later on, we'll see how it messes with base cases. It's just a lot cleaner if the empty string is not involved. Okay, so that makes a really nice and easy property that strings in the language K have to be non-empty. So let's try a few more basic examples. Let's say we just have a closed paren. That pretty clearly is not going to be a balanced string of parentheses. Neither is just an open paren. So already we can see that it's pretty clear that we need an equal number of open and closed parens. The most simple example is just having one open, one closed, and that should be in our language. So that's another property that we can list down. But this still isn't enough, because we can have one open and one closed, but if they look like this, that should not really be included in our language. This is definitely not a balanced string of parentheses. But at the same time, there's nothing special about having a closed paren and then having an open paren. We can come up with some more complicated examples, which include having a closed and then an open paren, but this actually is a balanced string of parentheses, so this would be in our language K. But still, things of this complexity sometimes aren't in the language K, so this is no longer balanced. So we have to try and figure out what kind of property would help us distinguish between a balanced and unbalanced set of strings. So this has 4 open and 4 closed parens, this one has 4 open and 4 closed parens, but there's something that differentiates this one from this one to make it balanced. So if you haven't figured it out yet, now is a good time to pause and walk through these two cases and try and figure out what makes one balanced and the other one not balanced. Okay, hopefully you've had some time and you have some intuition for what we're about to walk through. One way to look at this is as a scan from left to right. As we're scanning through this, we have to make sure that every time we have a closed paren, we're only closing a set of parentheses that we've already opened before. So for this one, every closed paren is matched with the corresponding open paren that has been opened to its left. If we look at the incorrect example, we notice that we open 1, we open 2, then we close 2, we close 1, and then we close something that we have not opened yet. So that's really where this goes wrong. If that explanation doesn't quite make sense yet, there's another way you can visualize this by making a mountain range chart. So let's start off by making a little grid, and I'm just going to go ahead and copy this string of parentheses that was correctly balanced and put it down here. And each time we see an open paren, we're going to take one step up in this mountain range. There's another open paren, so we take another step up. And whenever we see a closed paren, we take a step down. So following this pattern of going up and down, we end up with a little chart like this. Now when we look at the chart for the incorrect unbalanced string of parentheses, so let's go ahead and copy this one down in our chart, and we go through the same process. So this one opens and then closes, it closes, and then it closes one more time. And then it continues with an open paren, close paren. So both of these charts ended up in the same spot because they both had an equal number of open and closed parens, but somewhere in the middle, the example that was unbalanced went through the bottom. In other words, what we were really charting here was the difference between the number of open and the number of closed parens. When the difference went below 0 was when we had an unmatched closed parentheses. So that's really what we're looking for. With this in mind, there's a couple of different ways you can phrase this property. The way I find simplest is saying that as you're scanning from left to right, the number of open parentheses must always be greater than or equal to the number of closed parentheses that you've read so far in this left to right scan. Another way you could write this is that the number of open parentheses minus the number of closed parentheses is greater than or equal to 0. And that definition would match a little more closely with this mountain diagram visualization. Alright, so now we've defined our 3 rules. Let's go ahead and name them properties 1, 2, and 3. I know, super creative. And with that, we're done with part A. So we can go ahead and check that off and get started with part B. So for part B, we want to prove that a string X over this alphabet is an L if and only if it's in the new language K that we defined. So the language K we just defined is this, the language L was recursively defined as this, and we want to show that L and K are equal. So a language is really just a set of strings. If you want to show that 2 sets are equal to each other, what's the strategy you should be using? Hopefully this is ringing a few bells, and the strategy double containment comes to mind. In other words, we want to show that L is a subset of K, and K is a subset of L. So each one of these proofs, when we're doing the subset proofs, is going to require a certain strategy as well. Since L is recursively defined, that should give you a clue as to what strategy we'll need to use. And that strategy is induction. So with that in mind, let's get started with the first part. So in other words, we want to show that L is a subset of K, and let's go ahead and keep these definitions to the side for reference. Okay, we want to show that L is a subset of K. In other words, we consider some string S in L, and we want to show that that string S has to be in K. And we're going to do this by structural induction on L. So starting off with our base case. You'll notice when you're doing these structural induction proofs that your base cases normally line up really well with the base cases of the recursive structure. So our base case is actually going to be considering the string S as the base. So S is going to be equal to open paren, close paren, like the base case here. So we start off with our string S and L, and now we just want to show that this string S is also in K. And just looking at it, we see that it easily satisfies all these properties. It's definitely not empty. Then it's got one open and one closed. And as you do a left to right scan, the number of open is always greater than or equal to the number of closed. So we can see that indeed S is in K as desired. Awesome. So with the base case out of the way, let's get to the induction step. One thing to note is that when we're doing structural induction, we don't always explicitly write out the induction hypothesis because we assume that it's always going to be that the proposition holds for a structure with fewer recursive rules applied, so we just skip writing that down. For the induction step, we consider the string S made from the inductive rules. So the inductive rules are the wrap and concat rules. We already handled the base. So we can split this up into 2 cases. S was either made from the wrap rule or it was made from the concat rule. If S was made from the wrap rule, that means we know it was equal to open paren x close paren for some string x in L. Looking at S, we can clearly see that it's non-empty, so it satisfies the first property. It's got at least one paren in there. Now the question is, can we prove that it satisfies the other two rules? Since this is induction, a good starting point is messing around with X, the inductive part. So we know that X is in L. So we know then by the IH that X has to be in K as well. Since X is in K, that means it satisfies the properties for K. In other words, the number of open parens in X and the number of closed paren in X are equal. So we're going to use this notation to mean the number of open in X. So using this formula, we can just add +1 to both sides. And the number of open in X plus 1 is really the number of open in S, because we've got one extra open paren. And similarly for number of closed. So in other words, the number of open in S must be equal to the number of closed in S. And that's exactly what we wanted to show for property 2. So now let's get started on property 3. We want to show that in S, the number of open parens is always greater than or equal to the number of closed parens as you do a left to right scan. So let's start off by assuming for the sake of contradiction that this isn't true. In other words, the number of open parens is less than the number of closed parens at some point in the scan. The only way this can happen is if you read an unmatched closed paren, so that the number of closed parens becomes strictly greater than the number of open parens. Well, we know that this unmatched closed paren can't be the very last closed paren, because we already satisfied property 2, so the number of open is equal to the number of closed by the time we reach the last paren. But we also know that this unmatched paren can't be inside of X either, because X is in K, so it satisfies property 3. So if you just scan X throughout that entire scan, the number of open is greater than or equal to the number of closed. So when you're scanning S, all you've done is get an extra open paren. So as you're scanning it, there's no way that the number of open parens can be strictly less than the number of closed parens inside of X. So overall, there's no place for this unmatched closed paren. So there's no way for the number of open parens to be strictly less than the number of closed parens. In other words, we've satisfied property 3. Since we've satisfied all 3 properties, that means S is in K as desired. Awesome, so we're done with case 1. Let's get started with case 2, the concat case. In this case, we know that S is equal to xy for some x and y in L. Since x and y are in L, we can use the induction hypothesis on them, and we know that x and y are in K as well, so they satisfy these 3 properties. Since x is non-empty and y is non-empty, it's pretty easy to see that S must be non-empty as well. X and y also satisfy property 2. In other words, the number of open paren in X is equal to the number of closed paren, and similarly for y, the number of open in y is equal to the number of closed in y. Since S is just the concatenation of x and y, the number of open in S is equal to the number of open in X plus the number of open in y. And the number of closed in S is equal to the number of closed in X plus the number of closed in Y. Doing some simple substitution, we can get that the number of open in S is equal to the number of closed in S. Awesome, that means we have satisfied property 2. So let's get started with property 3. So assume for the sake of contradiction that we don't satisfy property 3. In other words, assume for the sake of contradiction that the number of open in S is strictly less than the number of closed in S at some point in the scan. There must have been some mismatched first bad closed paren that caused this to happen. This first paren could not be inside of X, because we know that when you're doing a scan of X, the number of open is greater than or equal to the number of closed. So if that ever happened within X, then X wouldn't satisfy properties 3 for K. We also know that it couldn't be inside of Y either. And this is because once you're done scanning X, we know that the number of open is equal to the number of closed. So then when you start scanning Y and the number of open is equal to the number of closed, if that first bad paren occurred within Y, that would mean that Y doesn't satisfy property 3 either, and Y wouldn't be in K. So that means this first mismatched bad closed paren can't be inside of X, and it can't be inside of Y, so it can't exist. In other words, we've satisfied property 3. So now, since we've satisfied all 3 properties, we know that S is in K just like we wanted. Okay, to recap, What we did here to show that a string S, when in L, must have been in K, we used structural induction, kind of mirroring the structure of L itself, and then for each case in L, we showed that the string S satisfied all three properties of K. So for each one of these cases, we kind of did three many-proofs to show that it satisfied all three properties, and we did that again for each individual case. So that was a lot, but we're not done yet, because we really only did one direction. We showed that L is a subset of K. We still have to go ahead and do the other direction and show that K is a subset of L. And let's go ahead and keep these to the side for reference again. So once again, if we want to show that K is a subset of L, we have to consider some string S in K and show that that string S is also in L. Since we're starting off with K, which is not a recursive structure, this time we're going to use strong induction on the length of the string. So let's start off with our base case. This is going to be when S is equal to the open paren, close paren. So the reason that we don't start off at, say, the length equal to 0, like we normally do induction on the natural numbers, is because this is the smallest string that satisfies all three properties. If you wanted to prove that, you could kind of do it in a brute forcing manner, that all strings of shorter length, the empty string, a single open, and a single closed paren, would not satisfy the three properties for K. So this base case is super easy because it perfectly matches this base case. So because it is that base case, we know that it must be that S is in L because it satisfies this rule. Awesome, so let's get started with the induction step. So now we consider S in K with length n greater than 2. This is where things get a little bit trickier. In fact, whenever you're doing these kinds of double containment structural induction proofs, this is the part which really requires the most creativity and thinking. What we want to do in this induction step is try and figure out a way to use the fact that we know that S is in K, we know that it satisfies these three properties, and use those three properties to somehow get S to look more like this so we can show that it's an L. In other words, we want to show that it satisfies one of the inductive rules now. So take a moment and think about how you might do that before we get started together. Alright, so what we're going to do is define this quantity V equal to the number of open paren in S read so far minus the number of closed paren in S read so far. And the reason we're going to do this is because it's going to help us split up into two cases, case 1 and case 2, kind of mirroring the way that L is defined in two inductive cases, wrap and concat. So you might remember that this value L kind of mirrors the mountain range diagram we had before. That's what we were plotting. Our two cases are going to be case 1, that the only time V hits 0 is at the very end. And of course, the very start always starts off at 0. And case 2 is going to be that V equals 0 somewhere in the middle of S. So to visualize this, let's start off with case 1. What this looks like is something like this. We always start off at 0, and then the only other time V hits 0 again is at the very end of the string. Visually, you can kind of see what this means, because we always start off with an open paren and end with a closed paren, and then we've just got some kind of mountain range string in the middle. So in other words, S is equal to open paren x closed paren. At this point, you might be tempted to kind of pattern match and say like, oh cool, it's the wrap rule. But we don't know that yet. We can only use the wrap rule if we can show that x is in L. And since we're doing induction here, in order to show that x is in L, we can use our induction hypothesis, and all we really need to show is that x is in K. Once we show that x is in K, we can cite the induction hypothesis and show that x is in L. So let's go through the three properties. Is x non-empty? Well, yes, it is, because S has length n greater than 2, so it's got more going on other than just these two open and closed paren, so x is definitely non-empty. Second, is the number of open in X equal to the number of closed in X? Well, we know that S is in K, and since the number of open in S is equal to the number of closed in S, and we just took away one open and one closed, it must be the case that the number of open in X is equal to the number of closed in X. So this property is satisfied as well. And for the last property, we need to show that as you're doing a left to right scan in X, the number of open is always greater than or equal to the number of closed. Well, we know that this scan property holds for S, And since as you're scanning from left to right, you start off with one extra boost of an open paren, that means as you're going through the scan, the number of open is always going to be greater than or equal to the number of closed. Visually, you can kind of see this boost. It's kind of like you just took x and you put it on stilts with the open and closed parens. So x satisfies this property too. Since we've satisfied all three properties, well look, x is in K as well. And since it's in K, we can cite the induction hypothesis and say that it's in L. And now we can use the wrap rule and say that S is in L because we've got some string x in L and we just wrapped it like this. So S is in L, just like we wanted, and case 1 is done. So let's move on to case 2. This is when V equals 0 somewhere in the middle of S. To visualize this using our mountain range diagram, this looks a little something like this. It could hit 0 multiple times, even though it's just drawn as hitting 0 once here. So now we're going to split S equal to xy, where we decide that split point between x and y as the first time when V hits 0. So in our visualization here, this part would be x and this part would be y. So once again, you might be tempted to pattern match and say that this satisfies the concat rule, but not yet because we still need to show that x and y are in L. And since we're doing induction, what we really need to show is that x and y are in K so we can cite the induction hypothesis. So the first question is, are x and y non-empty? Yes, they are. And this is because we know that S has length greater than 2, and we know that V equals 0 somewhere in the middle of S. Since it wasn't at the endpoints, we know that both x and y must be non-empty. The second question, is the number of open parens equal to the number of closed parens for both x and y? And this, once again, you can kind of visualize using our diagram, that because they're split precisely when V hits 0, that only happens once the number of open has hit the number of closed, which you can kind of get just from the definition of V. So for both of these, the number of open is equal to the number of closed. And lastly, is it the case that when you do a left to right scan for both x and y, the number of open is always greater than or equal to the number of closed? Well, we know that this property is satisfied for S, the overall string. So if this property 3 were false for x, then it would have to be false for S as you're scanning through. Similarly for y, because we split once V equals 0, then we can kind of restart our scan from there, and if this property 3 were ever not satisfied for y, it would not be satisfied for S either, but we know S is in K. So all three properties are satisfied for both x and y. So that means x and y are in K too, and therefore by the induction hypothesis, they are also in L. And now we can go ahead and use the concat rule and say that S is in L. So case 2 checks out as well. Just to recap what we just did here, is that we started off with some string in K, and then we used those three properties we had from K and kind of created our own cases to match up with the cases defined by the recursive structure. This is why this part of the proof often requires the most creativity. So this is where you'll come up with a way of matching the structure using some other properties. Awesome. Now we're done with the other direction of the double containment as well, and we can check that off, which means we are done with part B, and we are done with this proof.